I'd like to add a few closing thoughts on section 1.7, linear independence. And I'd also like to say a few things about the theorems that we didn't get time to talk about in class. When we're trying to determine linear dependence or independence of vectors, we can always set up a homogeneous system, AX equals 0, and solve. And whether we have only one solution or infinitely many solutions determines whether the system is independent or whether the vectors are independent or dependent. The theorems we were talking about give us shortcuts to avoid that process, which can be really long and tedious sometimes. So these shortcuts allow us to sometimes decide whether vectors are independent or dependent without having to go through a lot of work. Theorem 8 on the front side of our handout is one of the most straightforward shortcuts we have. So here I wrote some notes ahead of time. Theorem 8 really says the following, which I'm stating over and over again for different dimensions. If we're in R2, so two-dimensional space, any set of 3 or more vectors must be linearly independent. If you have more vectors than the dimension of the space, the set has to be dependent. So a set of 4 vectors from R3 must be linearly dependent. If you're in R4, a set of 5 vectors or more must be. Now it doesn't tell us anything about what would happen if we had less than or equal to the dimension of the space for our number of vectors. We'd have to use some other means to determine that. So that's theorem 8. Theorem 9 we didn't get to in class. That's on the top of the back side of the handout. Now there's a formal proof of theorem 9 there, but let's just talk about the idea. And theorem 9 is super straightforward. Theorem 9 just says whenever you have a set of vectors that includes the 0 vector, the set must be linearly dependent. So here's an example I wrote on ahead of time. There are 1, 2, 3, 4 vectors. These are all vectors in R4. Since it's 4 vectors in R4, we can't apply theorem 8 here because the number of vectors is not greater than the dimension of the space. But we don't even need theorem 8, because as soon as we see that we have that 0 vector in our list, it doesn't matter how many vectors we have, the set must be linearly dependent. So you definitely want to recognize that. You don't want to take this set of 4 vectors, set up an augmented matrix, and try to solve a system. You could, but that's way too much work, because it's obvious here, because of the presence of a 0 vector, that the set must be linearly dependent. And then I'd like to wrap up here talking a little bit about the wordy theorem 7 on the back side of the handout. It's really part A that's the most important, so don't worry so much about part B, but you should try to understand part A. A set is linearly dependent if and only if at least one of the vectors is a linear combination of the other vectors in this set. In fact, that's one way of thinking of what linear dependence means. Let me give you an example here. So I'm going to let v1 equal, this is going to be a vector in R3, 1, 0, 1. And v2 is 1, 1, 1. And I'm going to let v3, so I'm going to have a third vector involved here, and I want v3 to, I'm just going to call it 2v1 minus 3v2. So I'm intentionally defining v3 to be a linear combination of v1 and v2. So it's 2 times 1, 0, 1 minus 3 times 1, 1, 1, and it's pretty easy to go ahead and calculate what V3 is here. 2 times 1 minus 3 times 1, so that's negative 1 in the first position. 2 times 0 minus 3 times 1 is negative 3. 2 times 1 minus 3 times 1 is going to be negative 1 in the third position. So there's my V3 vector. Now, just suppose I looked at this set of vectors, V1, V2, and V3. 1, 0, 1, that's V1. 1, 1, 1, that's V2. And now I'm going to add to my list negative 1, negative 3, negative 1, that's V3. And suppose I wanted to decide if this set of vectors is linearly independent or linearly dependent. Now, if I don't know where these came from, I wouldn't know right now. It's 3 vectors in R3. I probably would go ahead and set up a homogeneous system of equations and solve. But because of the way we define this, I defined V3 as a linear combination of V1 and V2. So we can invoke theorem 7 here. I know this third vector is a linear combination of the first two. So that means this set must be dependent. That's really what theorem 7 is all about. Now I could have more than 3 vectors. I could have a higher dimension involved, but the same rule would apply. And it also means, it also tells us something about linear independence. If this was an independent set, then we could also say that none of the vectors in this set is a linear combination of the others. And finally, just a comment about the second part of theorem 7 from the handout. It's worded in a very abstract way, but it's really not saying anything that profound. The second part of theorem 7 just says when you have a linearly dependent set, so it could be 3 vectors, it could be 10 vectors, all it's saying is that as you work your way down the list of vectors, there's got to be at least one vector along the way that's a linear combination of the preceding vectors. That's really not so profound in light of what we've just observed about the first part of theorem 7. So that's it.